Hi everyone, we're going to pick up with 11.4 now, which is comparison tests. And there's actually two types of comparison tests that we're going to be talking about in here. So this is right after the integral test, and so we're just going to keep going with other various ways of testing to see if a series converges or diverges. So the basic comparison test says that if you have two series, the summation for the sequence on the A sub n, and that'd be this first one right here, and the series of adding up all the b sub n's are series with positive terms. So that's important. You do have to have positive terms here. If your series b sub n is convergent and b sub n is bigger than all the a sub n's, then your series for the a sub n also converges. Or the other way around, if your b sub n diverges and your a sub n is bigger than b sub n, then your a sub n also has to diverge. And so some people mix these up, so you have to be really careful. But you might remember a graph that sometimes is shown in Cal 2. You have two different graphs on here, and so you might have, notice you have to have positive terms. I'm going to stick with just the positive. Everything's positive in the first quadrant kind of idea. And so you might have a graph that is, maybe it looks like this, and it's kind of going down this way. We call that b sub n. And you might have another graph that's down here. That one might be a sub n. So our comparison test says that if b sub n converges, that's the one on the top. And b sub n is always bigger than a sub n. That's why it's above the a sub n here. So if the top one converges, the bottom one has to converge. Basically, you can think of it like the squeeze theorem in Cal 1. If the top one converges, it pushes the other one down to converge as well. Or the other way around, if you're diverging, then your a sub n also has to diverge as well. Determine if the series converges or diverges, and we're going to do this doing the comparison test. And so I need to pick a series to compare this to. So this series, the original problem, this would be your summation for your a sub n. I need a series to compare it to that would be a summation. That would be the b sub n part. And so the easiest thing to do, especially if there's something like 1 over n cubed plus 1, if there's something added or subtracted in the denominator, one of the easiest things to do is just drop off what gets added on. So could we possibly compare it to just 1 over n cubed? Well, you have to make sure our stipulation, you're only going to end up with positive terms, which is going to be true. If everything's added, you're going to end up with positive terms anyway. And then you also have to make sure that your inequality is correct. So our b sub n, we need to have that the 1 over n cubed and the 1 over n cubed plus 1, we have to compare what happens with those terms. And so here what we could do is just plug in a few numbers, see what happens. But you might be able to tell that the denominator of the 1 over n cubed plus 1 is bigger than n cubed because you're adding one more to it. And a bigger denominator is going to make a smaller fraction overall. So we're going to be going this direction. But you can plug numbers into it if you want to. You plug in 1, you would have 1 over 2 is less than or equal to just 1 over 1, which is 1. If you plugged in 2, you would end up with 1 over 2 cubed is 8 plus 1 is 9, which is less than 1/8. And so you could keep going. But it's not too hard to notice that the denominator on the left one would be bigger, and so the overall fraction would be smaller. I also need to notice what I picked 1 over n cubed for a reason, because I know that is a p-series. This 3 right here is greater than 1. And if you remember from your p-series that we talked about in the last section, if you're bigger than 1, this series converges because it's a p-series, as long as your power is bigger than 1. Remember, less than or equal to 1, it diverges, but greater than 1, it converges. And so now I know I have a convergent b sub n. So we're basically looking at this first one right here. If b sub n is convergent, which it is, and a sub n is less than or equal to b sub n for all n, which it is, then I know a sub n converges. So by comparison, the series must also converge, which is the answer. And so what you're just doing is you're trying to pick off a series you know will either converge or diverge, and then compare it and see what happens. So hopefully that's not too bad. We're going to do a few more of these. Okay, determine whether a series converges or diverges. So same process. This first one, the original problem here, this would be your a sub n. And I need to compare that to another series that I know something about. And like I said, if you have something where we have something added or subtracted to a denominator, the easy thing would be throw that off. And so I'm just going to do square root of n. And then this will be my b sub n. And so I want to compare those two things. I want to say, is 1 over the square root of n minus 1 compared to 1 over the square root of n, is it bigger than or less than or equal to? And again, here you'll notice we're starting the series at 2. That's only because we don't want to divide by 0. That's the only reason. Other than that, you could have started at whatever. But if you notice, we're here, the denominator of the left-hand side, you're subtracting 1 off. So the denominator on the left is smaller than the denominator on the right. And so since it's smaller, the overall fraction would actually be bigger. So here we're going to be going this direction. Oh, I don't know why I put the 2 there. Well, it's that as long as you have n greater than or equal to 2. You can also check it by plugging in numbers, but you do have to start with the number 2. So this would be square root of 2 minus, square root of 2 minus 1. This would be 1 over square root of 2 minus 1. That is indeed greater than 1 over square root of 2. You'd have to probably type that in the calculator if you wanted to do it. But if you jump to, like, say, 4, the square root of 4 is 2. So if I plugged in 4, I'd have 1 over square root of 4 is 2 minus 1 is 1. Is 1 greater than or equal to, plugging in 4, 1/2? And yes, it is. So the inequality is now going the other direction compared to the last problem that we did. Then I have to know something about this series. Well, it is also a p-series. Officially, a p-series has to start when n equals 1. So we could actually back this up and say that 2 was a 1, n equals 1 to infinity. But if you said n equals 1 to infinity versus n equals 2 to infinity, pretend like that was a 1 for a moment. This series would be a 1 over n to the 1/2. And that 1/2 would be your power, which is less than or equal to 1. that tells you that that series diverges. If it diverges starting at 1 versus starting at 2, won't make a whole lot of difference. If it diverges with all of those numbers added together and you add one more number to it, it's not going to make a whole lot of difference. And so I know that this series diverges by the p-series. Since that diverges, and my inequality says my a sub n is bigger than my b sub n, those two things together imply that my original series that I was working with, this series also diverges by comparison, comparing to the one with the minus 1 taken off. So this series actually diverges by comparison. Let's try another one. Determine whether the series converges or diverges. Again, this part right here is your a sub n that we're worried about. We're going to compare that to a different series. Now, notice here, there's something added or subtracted on both the top and the bottom. And so I'm actually going to compare it to dropping the 1 off on the top and the 1 off on the bottom. And I'm going to compare it to n over n cubed, which is actually the same thing as 1 over n squared. So I'm going to use 1 over n squared for my b sub n. And I'm going to compare the two. Is n minus 1 over n cubed plus 1, how does that compare to 1 over n squared? This one's a little harder to notice, but the one on the left, the denominator would be bigger than the n squared. The denominator is bigger, so the overall fraction is probably going to be smaller. Now the n on the top, the n minus 1, that will be getting bigger than the number 1 by itself. So if you wanted to compare it to the n over n cubed instead of the 1 over n squared, you'll notice that the numerator is smaller than that one. So this one's a little harder to just look at. So plugging in maybe 2, 3 numbers might be a good idea. If I plug in 1, I'd get 0 on top over 2, which is just 0. If I plug in 1 on the other side, I get 1 over 1, which is 1. Well, 1 is definitely bigger than 0. If I plug in 2, I'll get a 1 on top. 2 cubed is 8 plus 1 is 9. If I put a 2 on the other side, I'll get 1/4. 1/4 is most definitely bigger than 1/9. And you can keep going. If I plug in 3, I'll get 2 over 3 cubed is 27 plus 1 is 28, or 1/14. If I plugged in 3 on the other one, I get 1/9. So 1/9 is definitely bigger than 1/14. And so it's looking like our inequality should be this way. That our 1 over n squared is bigger than the n minus 1 over n cubed plus 1. So b sub n is bigger than a sub n. Again, I picked this particular series to work with because this thing is a p-series. I have a p being 2, which is greater than 1. So if it's greater than 1 for the power, this series has to converge by the p-series because the power is bigger than 1. And so if your b sub n converges, that would push down your a sub n to converge as long as b sub n is bigger, which it is. And so back over here, the original problem, this series converges by comparison. And that would be my answer to that one. Now, all of these that we've done so far are p-series, but you could do it with any series that you could absolutely figure out whether it converges or diverges with. Another example would be a geometric series. So this one actually I'm going to compare to a geometric series. Determine whether the series converges or diverges. Again, the 6 to the n divided by 5 to the n minus 1, that would be my a sub n. And I'm going to compare that to, since there's a minus 1 on the bottom, I'm just going to drop that minus 1 off. I'm going to make this 6 to the n over 5 to the n. Or this is 6/5 to the n. A geometric series has a times r to the n minus 1. This is almost geometric except for the fact that it just says n on the top. But we could actually fix that a little bit too. We could say this is 6/5 times 6/5 to the n minus 1. That would be your a r to the n minus 1. Now here, if you didn't notice that, your 6/5 would not really make a whole lot of difference. But if you were doing a summation to actually see what it sums up to, if you could find it, if it sums up to something, then you would want to pull that off. But anyway, I'm going to use this series right here. This will be my b sub n. And I want to compare that to a sub n. So we're going to compare the 6n over 5 to the n minus 1. How does that compare to whether you want to use the 6 over 5 to the n or the other one? It doesn't really matter. We want to know how those compare. Well, like on one of the other ones, we noticed the denominator here is smaller on the left than it is on the right, because the right-hand side would be just 5 to the n. The one on the left would be 5 to the n minus 1. So a smaller denominator means an overall bigger fraction. So I'm betting it probably goes this direction. But if you wanted to plug in some numbers, for instance, if you plugged in 1, you would have 6 over 5 minus 1. And if you plugged in 1 into the 1 minus 1 would be 0, so I'd have just 6 over 5. So 6 over 4 would be bigger than 6 over 5 because you're dividing by a smaller number. And you could plug as many numbers as you want to into it, but it will be going that direction. So your a sub n is bigger than or equal to your b sub n. I picked this series to work with right here because I know that since my r is 6/5, I know the absolute value of r, which would be the absolute value of 6/5, which is just 6/5. That's greater than 1. And on a geometric series, if your r is greater than 1, this series diverges because it's a geometric series. Oh, there's no e on the end of geometric, by the way. It's a geometric series with my r being greater than 1. Since that diverges, that series diverges, and it's less than the a sub n, basically what happens is the b sub n diverging pushes the a sub n up. And so this series over here, my original series, diverges by comparison. So hopefully that's not too bad. Okay, the second type of comparison test that you can do is actually called a limit comparison test. Here you don't really have to check to see if one series is bigger than or less than the other. Here we have our two series, our a sub n and our b sub n part. Again, they still have to be positive terms. So if we take the a sub n and the b sub n, we divide them and do the limit as n approaches infinity. If that comes out to a finite number greater than 0, then the series have to do the same thing. Either they both converge or they both diverge. So I want to pick a series that I can tell whether it converges or diverges, but instead of comparing whether one's bigger than or the other, I could divide the two terms, do the limit of it, and see if I get a finite number bigger than 0. So let's try one of those. Determine whether the series converges or diverges. So again, this part right here is my A sub n. So I want to pick a B sub n that I know something about. And so if I drop that minus 1 off, I would have 1 over 2 to the n, which is actually the same thing as 1/2 to the n. Or you could take it one step further to make it look like a really nice geometric series, where I'd have 1/2 times 1/2 to the n minus 1. This is your AR to the n minus 1. That's my geometric series. And so I know I can find something out about geometric series, whether it converges or diverges, and then I can compare the two. So, since this is geometric, my R, this little 1/2 right here, that is my R. So the absolute value of R is the absolute value of 1/2, which is just 1/2. It doesn't really change anything there. Which that is less than or equal to 1. That means this geometric series converges. This converges. This is a convergent series because it's geometric. And I keep wanting to put an E on the end of geometric for some reason. It's geometric with your radius or your ratio less than or equal to 1. So if it converges, I could divide the two series, and if I get a value, a number bigger than 0, then I could say that they both converge. And so that's what I'll do. I'll do the limit as n approaches infinity, and I divide the a sub n by the b sub n. So I take the 1 over 2n minus 1. Get that little extra little mark out of there. I don't know what that is. And divide that by my b sub n. And I'm actually going to use the 1 over 2 to the n just to make it look a little nicer. That way I can flip it over and have this say 1 over 2 to the n minus 1 times 2 to the n divided by 1. So the ones don't really matter, so I just get the limit as n approaches infinity of 2 to the n divided by 2 to the n minus 1. Okay, at this point, this is very much like what you would have seen in Cal 2, where we have a limit going to infinity. Your powers match on the same. We did this sort of thing probably with an exponential back in Cal 2, just like an e to the x or e to the 2x. But 2 to the n and 2 to the n, they are the same. So you technically get the ratio of what's in front of each one of them. You can notice this also if you want to work it out a little bit more detailed, that you're really going to get 2 to the n, and I divide everything in the problem by 2 to the n. That way what will happen is I'll just get 1 over 1 minus 1 over 2 to the n. And as you go to infinity, that denominator on the 1 over 2 to the n, this thing will actually go to 0. And so we'll just get 1 divided by 1, which is greater than 0. It is a finite number greater than 0, which means b sub n and a sub n have to do the same thing. And if they have to do the same thing, and I know the b sub n part converges because it's geometric, then I know this series up here at the top that I started with, this has to converge by limit comparison. Now, you might say, well, could you not have done it with a comparison test instead of limit comparison? Well, yeah, probably so. They're not guaranteed that you could interchange them because your inequality might be different doing the other way. And so if it doesn't work for one, try the other one. And my preference is not one or the other. It's just whichever one you feel like doing. And hopefully one of them works. Okay, let's do another one of those. And I'll do this again with limit comparison as well. 1 over the square root of n squared plus 1. 1 over n squared, 1 over square root of n squared plus 1. That part is your a sub n. I'm going to compare that to dropping the 1 off, the square root of n squared, which, because we're only plugging in numbers from 1 to infinity, we're only plugging in positive numbers, then the square root of 1 over n squared is literally just 1 over n. This is a p-series. Here, your p is 1, which is less than or equal to 1. This is actually, if you remember, this is the harmonic series, if you want to be precise, which diverges. The alternating harmonic series converges, but the just basic harmonic series will diverge every time. So if I can do limit comparison on this, if I know the harmonic series diverges, then the other one probably would have to diverge as well. So let's see. If I do the limit as n approaches infinity, and I do the a sub n divided by the b sub n, and for the b sub n, I'm going to just use 1 over n. If I flip that over and multiply it, I'll have 1 over the square root of n squared plus 1 times n over 1. And again, the ones don't matter, so I'll just end up with n on top. And on the bottom, I'll end up with the square root of n squared plus 1. Kind of like what we were talking about on the last one, you could divide everything by the highest power all the way across. Or, again, you could do what you did back in Cal 1. There's an n to the first power on top, and the n squared on the bottom is underneath the square root. So the square root of n squared would be n. So the power on top, the highest power on top, the highest power on bottom, they match. So the answer to this limit is just the ratio of the coefficients in front, which would be a 1 and a square root of 1, which is 1, which is greater than 0. And that's your stipulation. You have to be a finite number bigger than 0. And so since that's true, then the series have to do the same thing. Our b sub n diverges because it's a harmonic series. So my a sub n, this series right here, it has to diverge by limit comparison. And hopefully that makes sense. So we'll try one more. Determine whether the series converges or diverges. So this is n plus 2 over n plus 1 cubed. And I'll do limit comparison again. You are welcome to try doing the other way if you'd like to, practice them going the other direction as well with just comparison tests. But here my A sub n, all of this stuff right here. I'm going to compare that to, because there's a +2 and a +1 on the top and the bottom, I'm going to just drop those off. And I'm going to compare it to n over n cubed, which is the same thing as 1 over n squared. This is a p-series. This has a p of 2, which is greater than 1. So if you're greater than 1 on a p-series, this thing has to converge. This converges since it is a p-series, with the p being greater than 1. So if I divide them, hopefully I can figure out if they either go to a finite number greater than 0. Hopefully that works out. If it does, then I'll know that they both converge. So if I do the limit as n approaches infinity, and I do the a sub n, which is the n plus 2 over n plus 1 cubed, and I divide that by, I'm just going to use 1 over n squared. See what happens. I'll flip that over, and I will have n plus 2 over n plus 1 cubed times n squared over 1. So on the top, n squared times n will give me n cubed plus 2n squared. On the bottom, you get n plus 1 cubed. If you wanted to see it worked all the way out, you could FOIL that out. It would be n cubed plus 3n squared plus 3n plus 1, but you don't have to do that. I'm just going to leave it n plus 1 cubed. But the important thing to notice is that the power on the top and the bottom, the highest power on the top and the highest power on the bottom are the same. We have an n cubed on top and an n cubed on the bottom because of the cubed on the n plus 1. So the answer should be the coefficient sitting in front of those n cubes, which is a 1 and a 1 cubed, which is 1, which is greater than 0. You might also wonder, does it always come out to be 1 on the limit comparison, since that's what it's come out to be so far? The answer is no. It could be any finite number. It's just the easier ones usually come out to be 1. And since it's 1, which is greater than 0, then the series have to do the same thing. And so my series that I started with up here, this series has to converge by limit comparison, comparing it to the p-series that converges. So hopefully that makes sense. That's just a different way, another way to see if something converges or diverges, either doing comparison or limit comparison. And so that's the end of this section. We'll go on to the next section, which will be alternating series.